sidewalks, roads, all of that is contributing to the non-point source pollution. We have what we call the first flush. It's really big here in California. So I work in wetlands, and I'm not very scared to get muddy. But the one time I don't go into the wetland is after the first rain. So whether that's in October or December, depending on what year it is, that first flush, the first time that we have rain after a long summer of no rain, carries most of the pollution that you'll get into a system. It runs over PCH, it washes all that oil of 6 months off the road. I'm from Maryland. It snows sometimes there, but not all that often, so drivers are fairly bad about driving. It gets slippery, not very good. My equivalent here in California is the first time it rains. It's like everyone forgets how to drive. But there is also the backstory that that's the first time that 6 months of oil comes off the roads. It is legitimately a little more slippery here in California in the first rain, but that's the first flush I'm talking about. People have found that stream degradation occurs when it's surrounded by more than 10% impervious area. I can't name a stream here in urban Long Beach that has less than 10% impervious stream cover around it, which means that most streams in an urban ecosystem are going to be experiencing some form of degradation based on the surrounding amount of impermeable cover. What does that look like? I just have a diagram. This is from an urban watershed restoration manual. Sorry, that's not funny. Restoration manual. It looks at this type of impervious cover and where you have stream quality declining. So it's this 10% mark that we are classifying relatively high stream quality, impacted, non-supporting, and basically urban drainage. Most of our watersheds have urban drainage around here. There are ways to mitigate this. There are different pavers that can be used. There are bioswales, which can be planted around streams to filter out water. There's all sorts of restoration solutions around it, but for the most part, in our urban drainages, we're looking at this situation where we have poor stream quality, partially due to what's surrounding them. Yeah?
When you're saying that, do you mean that it's impervious right up to the edge of the stream, or so like the banks of the stream?
Yeah. I mean, it's the numbers on this chart are watershed wide, but some of the restoration solutions focus on the immediate surrounding area. So there's another chart that I didn't put in here that looks at distance, like buffer area around stream, and what that does to bump this number up. So like how far out do you have to restore to get an improved benefit? I wanted to just give you guys, again, for talking points, some examples of non-point source pollution sources and the potential contaminants. Septic systems, often leaky. They combine, bacteria, viruses, nitrates, compounds from household and personal care products. So one of the recent focuses has been on these sewage treatments also contain hormones and prescription drugs. So they're seeing sex changes in fish communities from the amount of estrogen in the water, that you have males becoming females. So in addition to what we're traditionally used to thinking about as contaminants, we now have a whole realm of pharmaceuticals that are coming in as well. Landfills, mines, these are contributing fairly typical compounds that we know about: heavy metals, nitrate, acid. Underground storage tanks are notoriously leaky sometimes. They're contributing, whatever they're holding, typically gas and fuel oil, as well as other organic chemicals. Agriculture irrigation, this is usually fertilizers, particularly nitrates and phosphates. They can also have pesticides. Automobiles, we're looking at metals, petroleum, hydrocarbons. Spills, you're looking at chemicals, whatever it is, pipeline leaks, animals, urban runoff. All of those, I just wanted to give you sort of a list of potentials. And there's a category where people have said, which one of all those non-point source and point source pollutions are we most concerned about? This is sort of the short list from a restoration manual of primary pollutants of concern. So this was a slide that Dr. Dahlman, who's in the geography department, gave me. She works a lot with waterbornes. And so she was identifying, these are the pollutants of concern that they're looking at when they describe a stream that's degraded or in need of restoration. Outside of pollutants, I put up the turbidity idea because this may be something that people are less familiar with. This is something that by Gestalt, a lot of people understand. Turbidity is water clarity. When you see a lot of suspended solids in a water system or sediment, you tend to have very, you could have degraded systems because there's a lot of runoff. How do people measure it? I just wanted to put this up as well. This is one of the simplest measurements you'll see a lot in water quality. It's called a Secchi disc. Basically, you have a line and a black and white disc that hangs off the bottom. You drop this down until you can't see the black and white anymore. That gives you a depth, it gives you a clarity. So it's a pretty simple measurement, a lot simpler than going out and being able to measure all those pollutants. But people find that turbidity and pollutants correlate fairly well. When you have highly turbid systems, you often have a lot of runoff, which means that you often have a lot of pollutants coming into the system. So you can use some proxies to understand pollutants more. And lastly, this biological indicators category. So there's a whole monitoring protocol in Southern California where people are going out and sampling streams all the time for all those physical and chemical parameters we looked at, and then for these biological parameters. So based on what invertebrate groups are present, we can correlate their presence with organic pollution because some of them are more tolerant to pollution than others. When it gets too polluted, they just drop out. They can't survive in that water. So we use organisms that are taxonomically sound. In other words, we know how to ID them very well. They're relatively easy to identify. They're numerically abundant. They're large enough to see. And we know their ecological requirements. We know that stoneflies and mayflies are not going to be in heavily polluted water. Caddis larvae, amphipods, these are both types of amphipods, tend to be somewhat tolerant, and by the time we've gotten to certain species of worms and fly larvae, they can survive in almost anything. So what you see is you see a reduction in diversity as you get more polluted, and you see one dominant species that can handle that pollution. So people go out and they take samples, and if you look, this is an example of my sample from a clean site. One thing is there's an abundant number of organisms and a high diversity of organisms. That tells us that it's capable of sustaining a large amount of life, and our indicator species like mayfly and stonefly are present. In the next sample, we've had some organisms drop out. In general, it's less diverse, less abundant, and we have a dominance maybe by these pollution tolerant. By the time we get down to the very polluted site, we almost have only pollutant tolerant organisms. And that's how people use biological indicators. There's indices where they can assign a number to these based on diversity, abundance, and species present. So any questions? That just gives you some vocab to look at water quality analysis, both in terms of chemical, physical, and biological indicators. Any questions about those? Okay. So lest we end on all the negative, I wanted to come up with some of the solutions. There are political solutions, which we started to talk about in the Delta example. How do you bring stakeholders together? How do you compromise? There are economic solutions that rely on economic principles. So it's more about the use of incentives and market-based principles to improve the efficiency of water use. There are technological solutions where you're attempting to work around the problem or treat the water or design a system where it can fit in water quality to your industrial process. And there are education approaches where you're really looking at integrating water management into people's everyday lives and just informing them about A, how much water they use, B, how they can use less or treat the water they use. This idea of integrated watershed management really is the first political category. So this is sort of the idea is what we were doing with the Delta example. We are basing resource management on dialogue and stakeholder participation. Instead of a top-down edict, we're saying we're going to coordinate this natural resource use with economic, social welfare, and ecosystem ideas. And this has become the way a lot of management is done. And we're trying to address it equitably. We're trying to weigh economic, social, and ecological ideas on